The title of this talk is A Unifying Framework for Fairness-Aware Influence Maximization. I'm Behruz Babaki, and this is a joint work with Gonush Farnadi and Michel Chandra. So everybody knows that nowadays algorithms have a much more central role than ever in our lives. It's quite often the case that the algorithms decide who gets a job, who goes to jail or not, who receives a loan from a bank, who gets diagnosed and receives healthcare. And with this ever-increasing influence of algorithms in our everyday lives, the question is whether these algorithms, whether these decision-making systems are fair. And this is actually a real concern, because over the past years it has been demonstrated in different cases how these algorithms can discriminate against certain parts of the population. For example, there's a well-known case in which it was clear that a decision-making system used for deciding who should go to jail or not discriminated against certain races. Similarly, systems used for recruiting were shown to discriminate against women, and so on and so forth. And this is actually a major concern, not just because of its ethical or moral implications, but also because there are laws against discrimination. So there are actually two main factors that govern these laws. One is about protected classes. So you cannot make discriminations based on certain attributes of people. For example, their race or color, their sex, religion, and things like that. And this will create things which are called sensitive attributes, the features of individuals which cannot be a basis for discriminating against these individuals. Also, there are regulated domains in which you're not allowed to discriminate among people. And a few of those are education, employment, housing, etc. And this slide shows the law in US, but a lot of other countries have similar laws. And now we're going to see how fair is a decision-making system in the setting of influence maximization. And we have to first introduce what influence maximization is. So basically, the assumption in influence maximization is that you have a directed graph, and every two nodes which are connected by an edge in this graph sort of have an influence on each other. This can be directed or indirected, so it can be symmetric or not. And you want to select a limited number of these nodes, say k nodes, such that the overall influence spread in this graph is maximized. And an example, for example, would be that you have a job vacancy, and of course you don't have infinite advertising budget, so you want to arrange that a few people would know about this job opening, and then they will tell others, and they will tell others, and this spread of news eventually makes it possible that a large number of people have heard of this opening. And the reason that fairness matters in influence maximization problems is mostly because several of applications of influence maximization are among the regulated domains which I mentioned earlier. So if you think about the problem setting that I described, you see that it will apply to healthcare, to advertising, political campaigns, marketing, etc. And you see a few of those are actually among those regulated domains. For example, the example of job vacancy is advertising, and you cannot discriminate in advertisement according to law. You cannot let only a certain portion of the population know of something and the others don't know, in a way that this portion is decided in terms of sensitive attributes. A similar thing happens with for example, distribution of healthcare. Suppose that you have some information, let's say, about how to prevent spread of a virus in a pandemic. And, well, you can only you have the budget to only give this information to a few people, distribute this information among just a subset of population, and you cannot discriminate and, for example, have it only distributed among people of a certain race. So there's a real immediate motivation for this problem that we study here. But before going further into the technical details, I should emphasize here that fairness is not a single unique criterion that we can just optimize for. At the moment, we're aware of 21 different definitions of fairness, and each of those are better suited to a certain situation. So fairness is not something general, and that actually motivates the kind of approach that we've taken in this work. We're not developing a method for a single fairness definition. We're actually trying to come up with a framework which we can use to actually incorporate varied definitions of fairness in the influence maximization problem. It's also worth mentioning that the fairness definitions can be broadly categorized into two groups. So one is group fairness and the other is individual fairness. Group fairness measures the impact of discrimination on groups of population and tries to eliminate this difference between populations. For example, you want some quality to be the same among, say, male subpopulations. Individual fairness, on the contrary, works at a more individual level. So it wants to ensure that similar individuals basically are treated similarly. Now we're going to move to the specific fairness criteria that are applied to the influence maximization setting. The first one that we introduce is a simple one, and it's called equality. So you remember that in the influence maximization setting, you have k initial individuals that you can target, and the spread of influence starts from those initial individuals. Equality wants to enforce that those k first individuals are more or less, there are more or less the same proportion of those among different populations. So roughly speaking, you want to have the same male individuals as the same female individuals. Or if there's a race which has an overall population of 3 times the other race, you want this proportion to be also reflected in the individuals that are selected as the source of influence. And these individuals are actually called the seeds because the spread starts from these individuals. Equity, on the other hand, is a measure that is concerned with the number of influence nodes. So once you've selected your seeds, the spread of influence starts and everyone receives this influence with some probability. So the equity measure wants to ensure that these probabilities are distributed more or less in the same ways in different subpopulations. Max-min is a measure which is related to the influence received by the least well-off group. So this measure basically tries to maximize the least received influence. And as you can imagine, by pushing the least well-off group, we hope to create a balance between different groups. Finally, the diversity measure assumes a scenario. So for each subpopulation, we can assume that we take the individuals in that subpopulation and isolate them from the rest of the individuals, and then we give them a proportionate amount of seeds, and then we will measure the influence. So it's like assuming if all females formed a society of their own and all males formed a society of their own, and we gave half of the seeds to females and half of the seeds to males, how much would be the influence received by everyone in the female subpopulation and the male subpopulation? And basically we want to arrange a way that every group is receiving at least as much influence as it would have if it was isolated. And this is not just for male and female, it's for every other grouping of individuals based on any sensitive attribute that we want. So some of these problems are studied before. As I mentioned, there are group fairness and individual fairness, and the measures that we mentioned were all concerned with subpopulations, so they're all group fairness measures. And in the past, two of these measures, max, min, and diversity, have been studied in a paper. And the solving method is to convert this optimization problem subject to these constraints or subject to this alternative objective to a series of multi-objective submodular optimization problems. It's also worth mentioning that individual fairness in influence maximization has also been studied. It has been studied just with the max-min criteria. So the goal is to basically maximize the influence that the least well-off individual, and not just the least well-off group, the least well-off individual receives. And this problem is solved by a number of heuristics. And these are the two works that we're aware of in this topic. Our approach is a bit different from these because, we, as I mentioned earlier, try to create a framework. So our work is much similar to the first work that I mentioned in the previous slide, concerned with group fairness. The way that we enforce these constraints, these fairness constraints, is that we formulate the influence maximization, so the basic, without any fairness constraints, we formulate it as a mixed integer programming problem, and then we show how each fairness constraint can be added as a set of extra linear constraints, or each fairness objective can be put there as a new objective function for this MIP problem. The advantage is that this is a general and extensible framework, and we also compare the performance of our method against existing approaches, and the results are promising. So let's start with how to encode the influence maximization problem in MIP. So the variables that we have are two types of variables. The first set are like one binary variable for every node, which we call SI, and it indicates whether or not that node is selected as a seed. So if S1 is equals to 1, it means that we have selected 1 as a seed. If it's 0, we have not selected it. And in this example, in this toy problem, you see that we have 5 S variables, and the budget constraint that says we can only have so much seeds is simply a linear constraint. So here the sum of SIs should be less than or equal to K. Then we have IP variables, which indicate whether a node is influenced in a sample. So P is the sample index. Basically, we take the initial graph and then we generate a number of samples from it. So here, for example, this is our initial graph, and we assume that we have created 100 samples. Then variable AIP indicates whether node I is influenced in sample P. Since every sample is a deterministic possibility, the fact that a node is influenced is deterministic, so it's either true or false. And the probabilistic part of the problem basically is reflected in the samples that we have. Now the objective function here is to maximize the overall spread, which means we want to maximize the sum of influences in all individuals in all samples. Now you see that the variable AIP is not binary. In principle it's binary, but it so happens that we can have continuous variables, and they will always have values 0 or 1. Now we should define the condition for a node to be influenced. Basically it's really simple. In a deterministic sample, a node is influenced either if it's a seed itself, or there is a path from a seed to it. So if I want to show it on this example, node 2 can be influenced if node 2 is a seed, or if node 1 is a seed. If any other node is selected as a seed, well, there's no directed path from those nodes to 2. And we can reflect this as this constraint, which says AIPA less than or equal, well, all seeds which have a path to AIP, basically. And so you can see that, as I said, for example, here, this is another example. Node, the fifth node is influenced if either it is a seed itself, so S5, or node 2 is a seed, which is S2, or node 1 is a seed, which is S1. And this is just for this sample. So we will have as many of these constraints for node 5 as there are samples. And then the same thing for every other node in the network. And all these constraints together will create the connection between the seeds and the influence nodes in all samples. Now, sometimes you need to emphasize that this relationship expressed by this constraint is an if and only if relationship, meaning that if a node is selected as a seed, or there's a path in that sample from seed to that node, it has to be influenced. With the influence maximization objective, of course, this is always the case because the objective pushes as many nodes as possible to be influenced, but sometimes with alternative objectives that we'll see later, we need to explicitly put this as a constraint, and this part in red basically enforces that this will always happen. Now we want to see how we can encode the fairness constraint mentioned earlier as linear constraints. We start with the equality measure. If you remember, this constraint said that the seeds dedicated to each group should be proportionate to the population of that group, and that's actually very easy. So you see that the main set of variables are the S variables, the seeds, and here the index J, a member of C, indicates that these are seeds belonging to group C, and these constraints basically enforce that the number of seeds belonging to this population is proportionate to the ratio of the size of this population to the size of the whole network. The next constraint is equality, and this constraint measures the similarity between the influence received by a population and the total influence received in the whole network. And for that, we basically establish a connection using the following linear constraint between the total influence received by the whole network, which is here, and the influence received by that population. And we will post this constraint for every population. The next constraint is the max-min measure, and well, this is actually more of an objective function, so we want to maximize the influence received by the least well-off group. So first we need to understand what is the smallest amount of influence received among groups, and we will encode that by this constraint. So xmin is the smallest amount of influence, of course proportionate to the size of every group, and this constraint says that this smallest value is less than or equal to influence received by a population divided by the size of that population. And then we maximize this value. Finally, there's the diversity measure, which wants to see how different is the influence received by the members of a subpopulation from the case that we isolate those members. And for that, we do this in 2 steps. First, we create isolated networks for all individuals. We we just run any influence maximization algorithm there, and we calculate the influence received in that case. And then we will run the influence maximization over the whole network. And for each subpopulation, we will add this constraint that says that the received influence in that population should be at least as high as the influence received in their isolated network. We conclude our work with an experimental evaluation. In this evaluation, we used 20 synthetic data sets, which have been previously used in similar studies. Each network has 500 nodes, and the number of edges are around 1,500 to 1,700. Each node is labeled by a number of attributes, and we group the labels based on their sensitive attributes, which is gender, which gives 2 populations, males and females, age, which gives 7 different populations for different age classes, and ethnicity, which gives 5 classes. Okay, let's first see how the MIP formulation of influence maximization compares against existing state-of-the-art algorithms. So here on the left, we have a few standard influence maximization algorithms, and on the right, we have the MIP formulation with different numbers of samples, 10, 100, 200, 500, and 1,000. And what we see here is, even though with an initial increase in the number of samples, the performance of MIP improves, after like 100 samples, MIP is already having a good performance compared to the state-of-the-art algorithms. Next, we're going to compare different fairness measures among 3 classes: gender, age, and ethnicity. So the dark bar here is the influence maximization algorithm, the coverage obtained without any fairness constraint, and then there are equality, equity, maximin, and diversity with respect to 3 different classes. And what we can see here is that the maximin measure has the least loss in coverage among different classes. We can also check the price of fairness, which is the ratio between the overall influence without fairness constraints divided by the overall influence after adding fairness conditions. And you see, it's similar to what we saw in the previous slide. So for example, here we see that age and equity has a high price, and we can make the same observation as before, meaning that maximin overall has like the least price of fairness. We also check different fairness measures in terms of L1 dispersion, which shows how close the values of influence in different groups are. And we can see that maximin and equity have the least dispersion. So the values in different groups are close to each other relatively when we're using these measures. Next, we're going to have a closer look on the maximin objective, and here we're going to compare our proposed method and the existing method for addressing this fairness condition. So in the plot above, MIP is the darker one, and the y-axis shows the least group coverage, which is something that we want to maximize. And as you can see, MIP always has a better objective. In the plot below, MIP is the light bar, and the existing method has the dark it corresponds to the dark bar, and here the y-axis shows the price of fairness, and you see that with MIP we're having a lower price, meaning that we're sacrificing less on the objective function in order to be fair. Next, we do the same comparison, this time with diversity constraint, and you can see again in the plot to the right that our formulation has better coverage, and the plot below shows the violation of constraints in the two methods, because there will be some degree of violation, even though we're solving the problem to satisfy these constraints. There's some probabilistic factor that makes this inexact to some extent, and you can see again that the MIP model has least violation of constraints, and also the variation between degrees of violations are also less for our model. So in the end, we finish our talk with these conclusions that fairness varying influence maximization is a relevant problem which is challenging. We exact the MIP framework, which is a general framework, an extensible framework for fairness varying influence maximization, and we show a few fairness measures that can be encoded in this framework. For future work, we want to extend our work to individual fairness. So this work was mainly about group fairness. We also want to evaluate our method based on real-world data sets instead of synthetic ones. We need to make this method more scalable to be able to apply it to larger graphs, and we also want to work on better sampling approaches which allow us to provide theoretical guarantees. Thanks a lot.